So I did want to start covering a little material today. We're going to do chapter 0 of this book, which is the introduction. And I've got a slide deck. And by the way, if you want the slide decks, they're all here on my page in PDF and in Apple Keynote format. So, all right. So here's my slides. And let's talk about this. I got a short lecture for the first day here because there's usually a lot of administrative stuff about people adding and things. So this is what we're going to do in this program, how C works and how computers actually work. You write in a high-level language like C or Python or Java, but computers can only run machine code, which is the code hard-coded into the processor. And so we're going to show how you translate C code into binary with a compiler, and how the circuits execute the binary encoding. And then we'll talk about how the operating systems manage programs. We'll get into the memory corruption vulnerabilities and examine the running programs with a debugger, so you see exactly how memory is used, and you understand the many security flaws of C, and we will exploit them. We'll cover primarily buffer overflows, but I plan to cover related things like format string vulnerabilities and others as we exploit these things to understand how memory is used and how it can be abused by hackers. And we'll cover the 3 most important kinds of assembly language: 32-bit Intel, 64-bit Intel, which are the current ones most people are using, and the up-and-coming ARM, which is what the new Apples are using. And it's pretty clear that there's going to be Windows ARM machines very soon if there aren't already, because Microsoft wrote a version of Windows 11 for ARM about a year ago, and they are currently writing a version of Windows Server 2025 for ARM. So in the future, both laptops and servers will probably all be running ARM, because ARM is faster and cheaper to run than Intel, and it creates less heat, and Intel has made disastrous business mistakes recently. Their recent processors have serious defects that they don't seem to be able to fix, sort of like Boeing. Intel seems to be going down, so ARM is coming up. So we'll cover all these. This is 32-bit Intel is the past, 64-bit Intel is the present, and ARM is the future. All right, so there's the free online textbook. That's what we're going to use. You don't have to pay anything, and it's a very nice textbook. Very nice of these folks to create it and hand it out for free. So today we're going to talk about hardware. We're not going to do much hardware here, but to cover a little bit, and then talk about what you'll learn in Linux, C, and the GNU compiler. So the components, you've got a program you run up here, and that goes to the operating system, which then goes to the hardware, which is the processing unit, the RAM, and the disk, although it's usually an SSD these days. And this is an important issue. Your program runs in what's called user mode. The programs that you launch from the start button or command prompt in your operating system do not have the privilege of fully using the CPU. In particular, you do not have the privilege to interact directly with any of the hardware. That's by design, because your program might crash. You might launching something up here like Firefox or Microsoft Word or something, or a game, and it might crash. And if it crashes, it cannot cause the entire system to stop, because the essential part of the system is still running. And then it can just pop up an error message saying your game has stopped, shall we restart it or something, because you don't have the authorization to do anything really serious. Down here is the heart of the operating system, and you don't have control over that. If you're using Windows, Microsoft controls this. You're using some other system, there's an operating system. So your program's running user land with a limited series of instructions, and when they want to use the hardware, they have to make API calls to the functions in the kernel down here in the operating system. So if I want to display something on the screen, I can't display something directly to the screen. Instead, I have to ask the operating system, will you please put this on the screen? And then it does it. So I cannot do anything arbitrary I want to the hardware. I can only do what the operating system allows me to do to the hardware. And I see a question there. When I take on the current controversy, yeah, well, I talked about that a bit. That's very interesting. The OpenAI, the Chinese DeepSpeak seems to be as good as OpenAI, very impressive and much cheaper. Yeah, and I'm making a video right now. All the videos will be posted on this page. So the same page where everything for the class is, and you go down to the schedule, and I'll put it right here in the schedule. As we do it every week, the videos will be posted here. And they're also on YouTube, that's right. But if you want to find them easily, go to the class website. They're public on YouTube, so anybody can see them. Good. I'm glad to see folks answering each other's questions there. It's very good. All right. So you got input-output ports that take data from the outside, like the keyboard and mouse, and then display it back by sending data out the network card and up to the monitor. The CPU runs instructions, and this is what we're mostly going to focus on is the instructions the CPU processes. RAM is what stores data and instructions, but forgets when you turn the power off. And therefore you need longer-term storage, and that's hard disks and SSDs, where you store data that remembers when the power goes off. The operating system is the software layer between the hardware and the user land software. So the user land software is sort of like an executive in the top floor of a building where they can make decisions and they can ask workers to do work, but they don't do work themselves. You tell your staff to go do something with their hands, like, build something or process mail or something, but you don't do it yourself. You just have to ask the workers to do it. You don't have the ability to do the work directly yourself. So this is where you see programming abstractions like processes and the file system, which are sort of illusions created by high levels of processing. And this means this has a huge consequence. Most developers of software do not understand the hardware, which is why it's very good for you to take this course and understand this. Most developers live in a world like Java, where you have arrays and strings and processes and load balancing and multi-threaded things, and you're worried about all that. And then you might be in a world of like graphic design where you're making a game look beautiful and adjusting the graphics and everything, and you work at that level and you never really think about the hardware, exactly what the processor instructions are like. And you trust the people that wrote your language and the people that wrote the operating system to take care of the hardware for you. And that's why it's often the case that the programmers create security flaws, among other things. So that's an issue. You can live at this high level. You could be like an artist doing computer graphics and never really understand the hardware at all and not really care. That's one possible way to be. But if you're taking this course, apparently you're in computer science and you would like to actually thoroughly understand the machine. And if you want to be a defender against hackers or a pen tester developing new attacks, you really have to understand it right down to the bits. And that's what we're going to do in this course. So general purpose reprogrammable computers are the most common type, of course. General purpose machines that can do anything. Yes, and N4C, you're quite correct. Things are unoptimized because the programmers work at a high level. And of course, to be fair, human effort is an important issue. So if what matters is you want to use less work for the programmer, then you work at a high abstraction level and you just let the hardware take care of it. And this is essentially what happened to the other topic that brought up OpenAI versus DeepSeek. America has been totally on this pattern of just making bigger and bigger hardware to where we're going to spend $500 billion having tens of thousands of expensive GPUs to run the large language models. And then we embargoed China so they couldn't get enough GPUs. And they said, well, since we can't get as much hardware, we're going to have to just be smarter about how we use it. And that appears to have been a tremendous success. They appear to have been much more intelligent about using weaker hardware to achieve excellent results at a much lower cost. And that has rocked us. So, that's the question. America seems to have been at the high level, not paying enough attention to the hardware, assuming we'll just throw more hardware at it and use our inefficient code. And China, having less access to hardware, decided to use it more carefully and apparently greatly more efficient. So a lot more of this is going to come out in the future. But it currently appears that China really has made their machine, their large language model 100 or even more times cheaper than ours and still have just as good results. And that means every company has to reevaluate their investment plans and their product development and everything else. Apparently, we're just a bunch of fools developing these monstrous data centers when we don't really need to. So that's the issue. All right, so general purpose reprogrammable machines are the most common, but then there's special purpose ones like calculators, thermostats, doorbells, smart light bulbs that just do one little thing, and they may have no operating system at all, although they might have a stripped down version of Linux, but they're not general purpose. So desktops and laptops, you're used to these things. There's a big battery in your laptop, a fan, a hard drive, RAM, and a DVD drive perhaps. All right, the kind of things you have in there. And then there's single board machines like Raspberry Pi and System on a Chip. It just miniaturizes all this thing into a smaller container. You can get these for like $10, and then you can easily build little gadgets. One of my friends builds trackers for satellites and automated satellite dishes, and she uses these microcontrollers and also prints her own components on 3D printers and writes her own custom software and builds radio antennas that track satellites because she secures satellites for Amazon. Anyway, and you can do all sorts of things here. People build their own firewalls, their own ad blockers, and their own little robot dogs, and just everything of these little cheap computers, which are very powerful and very small and cheap. So almost all the processors are now multi-core, so they can execute multiple programs simultaneously in parallel execution. All right. And so the operating systems you most see is Mac OS, which is a version of Unix based on Berkeley Standard Unix, and then Linux, which is very similar, running almost all portable devices like cell phones, and then Windows, of course, which used to be the dominant operating system and still is on some desktops, but increasingly Windows is a smaller piece of the market share, and Linux and Unix have largely won. However, Azure is very popular. A lot of people do use Windows. Certainly gamers mostly use Windows. Yeah, that's great. Yeah, somebody loves their Pi. A lot of people love their Pi. That's great. All right, so what we're going to do, we're going to talk about how you encode a program into binary, what a compiler does, and understand assembly and binary machine code. The central processing unit only understands binary. It has binary instructions built into the layout of the semiconductors on the chip that cannot be changed, and that's all your computer ever does is execute raw binary code. All the other languages you use are high-level abstractions that must be converted into raw binary machine code before they can run. The operating system gives you a user interface with a desktop, and it reads the mouse and the keyboard and opens up windows and such, and you control the program's execution, and it manages the resources. So when you double-click on something to open a browser, it allocates some memory to that process, launches the process, and eventually sends some instructions to the processor to make that happen. All right. So to figure out how efficient your system is, there are different algorithms you can use, and the course I was teaching last semester, which is the one before this one, was talking a lot about you can use more efficient algorithms that scale better for things like sorting. And then how the programs use system resources. It has to assign some memory to your program. And there are various ways to optimize code. We'll see a little bit about that when we get there later. We'll see how you can compile code, and then you can optimize code to make it into smaller assembly code that runs faster. And then you can worry about parallel computing for more complex tasks, which is a big thing in machine learning. That's why they're using GPUs that are highly parallel, where you have many processors all running separate jobs all at once. If you have a job that can be broken up into a lot of separate jobs, like you have an image you're processing, and you can break the image up into separate little regions and process each region separately. Or if you're trying to crack encryption, you're trying to try all values of a password or a key, and you can just break the keys up into regions and have many processors each doing a small bit of the key space. Trying to do the first project and won't let me type the password into the VM. Yeah, well, we'll check that out after this. I'll open up Zoom and you can share your screen and we'll see what's happening. I'm glad you're doing the project. All right, so Linux. I can tell you a little history, by the way. In the early days, like the 1960s and the 1970s, the only computers that existed were mainframes. They were very expensive, and when you bought a mainframe, you would get something like an IBM mainframe, and it would come with like 8 phone books worth of IBM information, and you would then have to learn IBM's mainframe language. But if you bought an Amdahl, you would have to learn Amdahl's language. And if you bought a Cray, you would have to learn Cray's language. And you could only program one type of computer with that language. They were not the same and not connected to each other. And this meant you had to specialize on one machine, and there was no way to share something between one machine and a machine of a different type. So computer scientists got fed up with this, and they said, we need to unify computers so they can talk to each other and work together. So they made the unifying operating system called Unix. Now, in order to do that, they had to have a language to write that operating system, and that language was C. And this all happened around 1979. So they would write C, and then they would write a C compiler for every piece of hardware. So you'd have a C compiler for the IBM mainframes, and a C compiler for the Amdahl, and a C compiler for the Cray, and all the other brands that existed. And once you had written those compilers, which had to be rewritten for each piece of hardware, now they could all run Unix, and Unix is written in C. It would run on all of them. So now you had unified the world of computers with Unix, and now you could invent the internet. The people in Berkeley invented Berkeley standard sockets, which defined TCP/IP and a way to communicate between Unix mainframes. And that created the internet, which started with 4 mainframes talking to each other across the United States, and of course expanded into the madness we know now. But it all worked that way. So Linux is just the home version of Unix, essentially. Essentially the same as Unix. You need C. And the GNU compiler is the most common compiler to compile C down to assembly code, and that's what we're going to use. And GNU stands for GNU's Not Unix. And a guy, Richard Stallman, made a big deal out of saying it's not Unix, it's technically something else. But then he's sort of been canceled for rampant, outrageous sexual misconduct. So I don't think anybody's pushing that much. But anyway, for all practical purposes, Linux and Unix are essentially the same. There are some small differences, but not enough to worry about. Right, so C is a high-level language. It is very close to the hardware. It's very close to assembly language. That's why we're going to use it. It's a lot closer to the hardware than more modern languages like Python and Java. It gives you more direct control over your hardware. It's like driving a car with a stick shift instead of an automatic transmission. You're really quite close to how it actually runs. And so we use the GCC, the GNU C compiler. That's what we're going to use, free and open source. This is the dominant compiler. And that's Linux, of course. Linux is big for superconducting machines. And, all right, if you're programming for Windows, you use the Visual Studio compiler typically, but the end result is very much the same. All right, so I'm going to do a Kahoot today. This is a way you can get some extra credit. It helps wake people up after a lecture. It's a little video game-like thing, like a contest. So what you do, let me get it started here. You do not need to do this. It's optional, but people usually like to do it. It sort of wakes them up. Okay, go to kahoot.it and put in that number and a name. And then you can compete in a little quiz here. And if you get in the top 3 of scores, you get 3 points. And it can add up to a lot after a while. So it can improve your grade a bit. But the main thing is it just keeps people from falling asleep. And by the way, you can use any name you like, but if it's not close to your real name, you'll have to tell me who you really are if you win, or I won't be able to give you your points. So, I'll wait a bit. Usually, especially the first time, it takes a while for everybody to get in here. I see. Zooey Edwards says C on an Arduino is closer to hardware than on Raspberry Pi. Could be. I've never programmed an Arduino. I've heard about them. Yeah, it would be nice to have some projects for Arduino and Raspberry Pi. Maybe I'll do that. I do have some, actually. One good thing about the Raspberry Pi is it's a chance to get your hands on some ARM hardware. By the way, I might as well mention, in addition to ARM, there's RISC-V, which is the open source competitor to ARM, and it's becoming very popular in China because of US's extremely unwise embargo of technology with China. So there will probably be RISC-V machines coming out soon. Although it's very similar to ARM, it is technically open source, open availability. You don't have to pay a licensing fee to use RISC-V hardware the way you do for ARM. All right, Well, I think we got everybody. Let's do this. All right, so what component is between the program and the hardware? All right, that's the operating system. Good. By the way, it rates you not only on whether you got it right, but how fast you got it right. So you'll see the score. You can get up to 1,000 points for each question. So you see Michael was the fastest. All right. All right, which of these is not a high-level language? Yeah, assembly is the one that's not a high-level language. All right. And by the way, the Kahoot will be sending these questions to you live probably before you see my Twitch. The Twitch stream has like a 5-second delay, which you can probably notice while this is happening. All right. All right. So which item translates C to machine code? All right, and that's GCC, the GNU C compiler. So here's the winners. All right, question mark will clearly have to tell me who they are if they want their points. KT might be enough to identify that person with initials and might not. And Michael, again, that might not be enough to uniquely identify you. So if you want to make sure you get your points, you ought to tell me who you are. I'm going to stop this recording.